If all PIs are assumed equal, which is unlikely but useful for approximation and computation purpose, then you can generalize and write F is equals to N into P. So equation number 4 is very important here in order to find what is the frequency of line stops. Okay. But here we make an assumption that all the values of P, that is the probability of failure of every station, it is going to be equal is what is assumed here. And that assumption is basically made in order to get a proper approximation and for computation purpose. So based on this consideration, or based on this assumption, we have F is equals to N into P. So F can be obtained by knowing the number of stations into the probability of failure at each station. Okay, again, I'm repeating, it is assumed that p value is going to be same for all the stations. If the p value is not the same for all stations, then the way in which you calculate f is going to be different. So we'll see that. Just complete these equations. Completed the equations?
Yes, ma'am.
Okay. So as I said, if the probability of failure at every station is considered to be equal, then you can calculate f, that is the frequency of line stops per cycle, by using this equation f is equals to n into p, where pi are all equal, like p1 is equals to p2 and so on up, that is summed up to, oh sorry, that is equal to p. But equation 4, that is f is equals to n into p, it is applicable only if the probability of failure is same for all workstations. If the probability of failure is different for individual workstations, then the frequency of breakdown, it is given by this equation. F is equals to P1 plus P2 plus P3 and so on up to Pn. So it's simple to understand and remember. If you consider P to be equal, it is number of stations into P. If not, it is the sum of all the probabilities, depending upon the number of stations. So we have it. Good. Completed?
Yes, ma'am.
Any doubts still here? No doubts? Shall I proceed? Okay. So now we have this performance measure. What is the performance measure of our concern here is the production rate. So we already know how to find the production rate. We are just repeating. So one of the important measures of performance on an automated transfer line is the production rate, which is the reciprocal of 1 by, reciprocal of TP. So we know already how to find the production rate, that is 1 upon TP. It is of interest to compare this rate with the ideal production rate. Production rate here, it means that with all the practicalities in place, considering all the breakdowns, considering the amount of time it actually performs all the tasks, based on that you have RP is equals to 1 by TP. But then there is something called as the ideal production rate, that is RC. RC is given by 1 by TC. This is what is expected, or yeah, it is what this is what is expected when you assume that all the conditions are well in control. It has 100% efficiency and all. That time you go for this ideal production rate, that is 1 by TC. RC is equals to 1 by TC. So we have this equation where RC is ideal production rate, pieces per minute. So it is a customary to express production rate on automated production line as hourly rates. So we multiply RP by 60. So we are all are very well aware of this, that production rate, it is usually expressed as hourly production rate. So you use this constant 60 in order to convert minutes to hours. Now let's see what is this lower bound approach. In this type of approach, the station breakdown results in damage of part and it must therefore be removed from the line. So I hope you can now understand the difference between the upper bound approach and the lower bound approach. When it comes to upper bound approach, the work part is not getting affected in any way even though the workstation stops. Whereas in lower bound approach, the work part is getting affected. It gets damaged in a way. For example, maybe you have this production line going, and at some point of time the tool breaks. And when the tool breaks, the workpiece is getting affected. Maybe the surface of it gets damaged. Okay. In that case, the part cannot be moved ahead to different workstations. Whereas if you consider the upper bound approach, which we have seen initially before this, suppose if there is this work part at one station and there is power failure, the work part is not getting affected in any way. Okay, it is not getting damaged. You don't have to throw it off. You don't have to scrap it off. You can still wait for that problem to be rectified, and that work part will still get processed and moved to the next station. Whereas in lower bound approach, that does not happen. That part gets completely damaged because of some major issues for the breakdown, and it has to be removed from the line. It will not be sent further to the downstream stations. So the lower bound approach, it arises in situations such as tool breaks during processing, which may result in damage of part. In such cases, the broken tool must be replaced at the workstation and the parts must be removed from the line and cannot proceed to the next station for further processing. So this is what is lower bound approach. Lower bound approach, the work part gets damaged because of XYZ reason, and then it will not be moved to the downstream station. That work part will be scrapped off. Whereas with respect to upper bound approach, the reason for the line stop may be some minor reason, not very serious reason. Maybe there is some power failure or something like that. The work part still remains on the station and it waits for the things to be rectified, and then it will be moved ahead to the downstream stations. So in lower bound approach, in case of lower bound approach, the frequency of breakdown is given as, please note down this, it is 1 minus p to the power of n. So here you can understand the difference for upper bound and lower bound approach. You have different equations to find the frequency of breakdown. F with respect to upper bound approach, it is given by n into p, assuming that all the p values are equal. And for lower bound approach, f is given by 1 minus p to the power of n, where n is number of workstations and p is probability of failure in each workstation. So the above formula is applicable only if the probability of failure is same for all stations. Just as we saw in the previous case, where f is equals to n into p only when p values are equal. So is the case here also. Assuming that all the values of p are equal, we get f is equals to 1 minus p to the power of n. In lower bound approach, the parts are removed from the line. The number of parts coming out of the line will be less than the parts entering into the line. So it's obvious that because of some sort of breakdown, which causes damage to the part, the number of parts entering the line will be less than will be more than the number of parts leaving the line, right? Because the parts are getting damaged. So therefore the production rate formula will be changed to reflect the changes in the output. So we already know one of the performance measures where R is equals to 1 by TP. So here you will see that the value of R incorporating the damage that is happened, you get Rp is equals to 1 minus F upon Tp. So with respect to upper bound approach, the equation for F and Rp are different. So please write down clearly under upper bound approach how you can find F and Rp. Under lower bound approach how you can find F and Rp. So if the probability of failure is different for individual workstations, then the frequency of breakdown is given by. So this equation, what you see here, F is equals to 1 minus P to the power of N. If the value of P is equal at on stations, then you use this equation. If it is not, then you can find out F with this equation. 1 minus the answer of 1 minus P1 into 1 minus P2 into 1 minus P3 and so on up to 1 minus Pn. 1 minus the answer that you get for the substitutions in the bracket. I hope all of you have noted down these points.
Yes, ma'am.
Okay, any doubts so far? Because you have to solve problems based on this. So this is very important. You have to practice all these equations.
No, ma'am.
Okay. So it's either you're understanding or nobody's actually listening when you don't have anything to ask me. So I'm assuming both the conditions and I will proceed. So the transfer line, because of downtime, will not operate at 100% efficiency. So we are very well aware of this fact that the transfer lines that we have, anything, any of the systems or anything that you see is not going to have 100% efficiency in its performance. So what happens? The machine tool builders that are there, they basically use this ideal production rate (RC), that is 1 by TC, in its proposal for automated production line and speak of it as production rate at 100% efficiency. But unfortunately, what happens because of all these downtimes, the line will not operate at 100% efficiency. While it might, it at times seems like those machine tool builders are breaking our trust by saying that they are providing us 100% efficiency. But basically, that's not the reality. You will not have this 100% efficiency in most of the cases because these machine tool builders, they often ignore the effect of downtime on production lines and they just claim that it is going to be 100% efficient. Um, so what happens? The amount of downtime that we experience, it is basically said to be the responsibility of the company which is using the production line. Then the person who is providing you or the machine tool builder, basically it should have been his responsibility, but in practicality that's not the case. The company who is using it is going to be responsible for it. So in practice, most of the reasons for downtime that we have already discussed, they represent the factors that must be controlled and managed by the company. So I already said there are so many reasons for the downtime to occur. There is failure at the workstation, maybe there's power failure, maybe there is worker breaks that happen, some electricity malfunctioning, some tool adjustment, tool failures. So these are so many reasons that lead to the breakdown of a workstation, and this becomes the responsibility of the company to control all these reasons, which may lead to some of the breakdowns, which may lead to breakdowns. So line efficiency now becomes important here. So in the context of automated production system, line efficiency, it refers to proportion of uptime on the line and is really a measure of reliability more than efficiency. So let us see how we can calculate line efficiency. Line efficiency, it can be calculated with the help of this equation. It is Tc by Tp. That is usually what is expected and what is the actual status, right? Tc is ideal upon Tp is what is what is that you get. So Tc, we know Tp is equals to Tc plus F into Td. You can look back into the equations that you will have noted down today. You see Tp is given by F into Tc plus F into Td. So the equation for line efficiency is equation number 7, that is Tc upon Tc plus F into Td, where E, you can call it as a line efficiency or it can be the proportion of uptime on the production line. Uptime is what? The actual time available for all the operations to happen. And downtime is the time for which it is going to be off. It is not working. So an alternate measure of performance is the proportion of downtime on the line which is given by. So we have these two equations which one gives you the uptime and one gives you the downtime. So you can get any of these. There can be questions which ask you to find out what is the uptime, that is efficiency, or they can ask you to find what is the proportion of downtime. And this proportion of downtime, it is given by the equation D is equals to F into Td upon Tp. So that is equation number 8, where D is proportion of downtime on the line. And it is obvious that the sum of E plus D should be equal to 1. That is the time for which it is actually working, or you can say the efficiency when everything is going smooth, plus the time for which it is going to be off. The total has to be summed up to 1. So E plus D, the value answers that you get for E and D should be equal to 1. Just note down these two equations for E and D, that is proportion of uptime and proportion of downtime. All have completed these equations? Yes? Anybody there, or my lectures are just getting recorded?
No, ma'am. Done noting down.
Okay, write down. If this is the response I'm going to get from all, I better stop recording the classes so that you all can attend instead of waiting for the recordings.
Ma'am, when will you share this PDF?
Huh?
When will you share this PDF?
I can't hear you. Could you be a little louder?
When will you share this PDF?
After I finish this unit.
Okay, ma'am.
Yeah. Anyways, I'll share it today itself. Whatever little is left out, no, okay, this is for everybody. Uh, Based on the time frame that we have, I will just be discussing one problem each in this analysis part. These are the solved
Okay.
examples that I'll be discussing. But I will give in the form of notes the unsolved problem solution. I will not discuss them. If any one of you have doubts with respect to the problems, you all can get connected with me. I will just provide you the solutions for maybe one or two unsolved problems from the textbook with respect to both the conditions, one with the storage buffer and one without storage buffer. So that because of this time frame, I want to start with the third unit and you have your internals also. And we are already lagging behind because of my other work commitments. So those notes will be shared with you only with respect to the problems. Otherwise, the theory part, anyways, I'm discussing. I hope this will be fine with you all.
Ma'am, is
Yeah,
theory written in the notes? Is theory written in the notes?
I could you please repeat? I couldn't hear you properly.
You said numericals are there in the notes, but what
Hmm.
about the theory? Is it shortly written
Theory
or
I'm completing. Theory I'm completing.
no? No,
Theory
I
part
mean,
will be completed. I had this practice of solving unsolved problems also with you all, right? I used to discuss the unsolved problems also in the class.
ma'am, what I meant is
Huh.
theory written in the notes? Is it available in notes?
Yeah, whatever I'm discussing now here in front of you on the slides itself is the theory that I have written, or else you can
Oh,
refer to the textbook.
okay, okay, got it, ma'am.
Okay, there is no other because I think the theory that I'm showing you people in the class itself is a very exhaustive theory. There's
Okay,
hardly anything that I must have missed out.
okay, ma'am.
Okay. Okay. If you consider the core theory part of this unit, which is in the very starting of the chapter, for more content, you can refer to the textbook. But when it starts from the analysis part, this much should be sufficient. Whatever I have written, no, that is sufficient for analysis part.
Got it, ma'am. Okay.
Only the unsolved problems I'll give in the form of notes. You all can solve them on your own. Any doubts? Get back to me. Okay. So proceeding. An important, okay, till now, so we have seen how to calculate TC, we have seen how to calculate TP, then we saw what is upper bound, lower bound approach. In upper bound approach, we saw how you can find out F and RP. In lower bound approach, also we have seen how we can find F and RP. And then we saw the equations for line efficiency, or we can call it as the proportion of uptime and proportion of downtime. Now we will proceed to know yet another important measure of performance. This is an important economic measure of performance of an automated production line, and that is the cost per unit produced. So, cost is very important factor for all the industrialists, for any of the company. All everybody aims at reducing the cost, or based on the amount that they are going to spend or invest, all their other decisions will be based, right? So this is a very important economic consideration or a parameter of measure to measure the performance. So here this piece cost, okay, that we are going to calculate, it includes the cost of starting material that is to be processed on the line, the cost of time on the production line, and the cost of any tooling that is consumed. So when it comes to calculating the cost of a part, one part that comes out of the production line, that cost is going to have the sum of all of these elements that I just read. That is the piece cost, that is per part cost. It will include the cost of starting material, that is raw material, the cost of time of production line, and the tooling cost. These are the three things that will be added in order to get the cost of that particular part. So the piece cost can be expressed as a sum of these three factors. What are those three factors? It's here. CPC, that is cost per piece. It is the material cost CM plus the operation cost into TP plus the cost of tool or the tooling cost. So just write down this equation where CPC is cost per piece, dollars per piece. CM is cost of starting material. C naught is cost of minutes to operate the, sorry, cost per minute to operate the line. EP is average production line per piece, and CT it is cost of tooling per piece. Completed equation. So this equation that you see, it only has these three major factors taken into consideration, like the cost of material, the tooling cost, or the actual production cost that is there. We are not taking into consideration the scrap rate, or there is no inspection cost or some rework cost. All of these things are not taken into consideration here, but you can even consider those to get a still accurate cost of per piece. But this, it is in general, that is equation number 10, which has the major factors taken into consideration. Okay. So I assume that you all have written down the equation, and I'll proceed. This is one solved problem from the textbook. I'll just discuss this problem. Okay. The problem statement is as follows, and it is problem number 16.2 from the textbook. I'll read the problem statement. A machine tool builder submits a proposal for 20 station transfer line to machine a certain component currently produced by conventional method. So you can just write down the number of stations is 20. Okay. Next is the proposal states that the line will operate at a production rate of 50 pieces per hour at 100% efficiency. So RP, it is given as 50 pieces per hour. On similar transfer line, the probability of station breakdown per cycle is equal for all stations, and P is equals to 0.005. So the problem statement says that the probability of failure at all stations is equal, and it is 0.005 breakdowns per cycle. It is also estimated that the average downtime per line stop will be 8 minutes. So average downtime is given by TD, and it is given as 8 minutes. The starting casting, that is machine on the line, will cost rupees 3 per part. So rupees 3 per part, the starting costing, that is CM, that is cost of material that we have, rupees 3 per sorry, dollars, $3 per part, and it operates at a cost of $75 per hour. So C naught, that is operating cost, it is $75 per hour. There are 20 cutting tools, so it's written here 20 cutting tools. They last for 50 parts each. So 20 cutting tools, they are going to last for 50 parts each. That means one cutting tool is capable of machining 50 parts, and the average cost per tool is $2 per cutting edge. Based on this data, compute the production rate, line efficiency, and the cost per unit piece produced on the line. Okay. After this, please write down one more statement. You have to solve this problem by using upper bound and lower bound approach, both. You have to find the production rate based on upper bound approach and lower bound approach. And then you have line efficiency. You have separate equations to find line efficiency. And then you have a separate equation to find the cost per piece. So when you compute, you have to find production rate with respect to upper bound approach and lower bound approach, and line efficiency separately. And then you have CPC, that is cost per piece value. So just start solving. This is already, the given data is already given to you. So the production rate, if you consider, if you start with upper bound approach, it is given by 1 upon TP, right? Or 60 divided by TP. So you know how to find TP. TP is equals to TC plus F into TD. Or else just do one thing, you solve only by the upper bound approach. Don't solve by lower bound approach now. Later on, you can solve the same with the lower bound approach and see how things are different. So as of now, you only solve it with help of upper bound approach. We know RP is equals to 1 by TP. And we know dP is given by dC plus F into TD. At 100% efficiency, the line produces 50 pieces per hour. The reciprocal gives the unit time and ideal cycle time, or the ideal cycle time per piece. So we know RP value is given to us. We can find what is TP. Having known what is TP, we can find out, and also given what is TD. F can be found out by using N into P. You can find what is TC here. So just substitute and find out what is TC. Okay, so in this problem, we don't have to go with all these substitutions. In the problem statement, it is mentioned that the automated production line is having 100% efficiency. When it is assumed to be 100% efficient, that means the given value is not RP, it is the ideal production rate RC. So having known RC, we know RC is 1 by TC, and TC can be obtained with this. You don't have to go for all these substitutions or finding the unknown values. You can directly get the value of TC by using this equation. RC is equals to 1 by TC. Is it clear? So you get this as the TC value. So they have not given what is the actual production rate. They have given you the ideal production rate, that is RC. You have to find what is RP. All of you have got this value of TC? Yes? Okay. So we know P is equals to 0.005 given. From this P, we can find what is F. F is equals to N into P. You get the value of F. We know number of stations is given as 20 workstations. I told you at the start of the problem, 20 workstations. So you get the value of F as 0.10 breakdowns per cycle. So having known the value of F, we already know the value of TC. We know the value of F now. TD is already given. You get the value of TP and then you get the value of RP. So average production time per piece, TP, is TC plus F into TD. We know TC is 1.2 plus 0.10 into 8. So TP value is 2 minutes per piece. Hence, the actual average production rate is going to be 1 by TP, that is 0.50 pieces per minute. Completed this? Okay, I assume that you have already finished writing this and I'll proceed. So RP value is 30 pieces per hour. Now we have to find what is the line efficiency. It is given by TC upon TP. We know the value for TC as well as TP. It's simple direct substitution. You get the value of E as 0.60, that is 60%. Moving on to the last part of the problem, we have to find what is the cost per unit piece is produced on line. So cost per unit is given by Cm plus C naught into Tp plus Ct. So already we know the value of Cm, we know the value of Ct also can be obtained. We know the value of Tp, but we do not know what is C naught. Okay, sorry, C naught is also given. Sorry, CO is also given. So let's find what is the tooling cost per piece. Okay, you have to find it. We know that there are 20 tools. Each tool cost is $2 per tool, and you have 50 parts. So you get the value of CT as 0.80 per part. Then you go for direct substitution to get the answer for cost per piece. It is 6.30 per piece. Okay, so this problem ends here. I will not be continuing with this, but I will just explain these two concepts of starving and blocking here, and then we can stop. Okay, so we have just discussed the transfer lines with no internal storage buffer. So whenever you do not have a storage buffer in place, then what happens is you assume or rather it is like the complete production line is going to be very much, there's lots of interdependency. So breakdown of one station results in the failure of the complete production line. But suppose if you are including a internal storage buffer at some locations in the production line, things can be well controlled. So there are these two important concepts that we need to know here. One is the concept of starving and one is the concept of blocking. I've just briefed you about this previously also when we were discussing about the storage buffer. So what happens is, when one station breakdowns, all other stations on the line are affected. They are either immediately or by the end of the few cycles of operation. Because of starving and blocking, they get affected. So what happens? These terms that we are studying, starving and blocking, they have the same meaning in production line, also in the assembly lines. So starving on an automated production line, it means that a workstation is prevented from performing its cycle because it has no part to work on. Starving, it actually, you know the meaning of starving, right? When you don't get food, you starve. That's what we, that's what is the meaning of starving. The same happens with that particular workstation also. When it is not getting the parts to work on, we call it as starving. So here what happens, when a breakdown occurs at any workstation on the line, the downstream station will either immediately or eventually become starved for parts. And what is blocking? Blocking means that a station is prevented from performing its work cycle because it cannot pass the parts just completed to the neighboring downstream stations. So blocking is the literal meaning that we know. Things are going to get blocked because they cannot be moved further. When a breakdown occurs at a station on the line, the upstream station becomes blocked because the broken down station cannot accept the next part for processing from its upstream neighbor. Therefore, none of the upstream stations can pass its completed parts forward. So, if one station breaks down, it cannot pass the parts forward to the next station. Rather, all the parts from the previous workstations, preceding workstation, they will just go on moving it until that workstation which is broken down and everything gets stopped up there. Everything gets blocked there. It cannot move further. So that's the concept of blocking and starving here. So downtime on an automated line due to starving and blocking can be reduced by adding one or more part storage buffers between the workstations. So in order to avoid this problem of starving and blocking on an automated production line, you can accommodate the buffer storages, or we call them as the storage buffers, in between the stations. Now you want to have the buffer storage after how many workstations? It depends upon the company. You can have a buffer storage after every workstation, or you can have it after certain fixed number of stations. So storage buffer, it divides the line into stages that can operate independently for a number of cycles, the number depending on the storage capacity of the buffer. So as I said, you can have a buffer storage after every workstation, or you can have them after a number of workstations. So those number of workstations will be called as stages. So if one stage buffer, a storage buffer is used, the line is divided into two stages. So suppose if you consider an automated production line of 10 workstations and you want to divide them into half, 5 plus 5, then the first 5 stations will be called as one stage, then you have a storage buffer, and then you have the 6 to 10 workstations, they will be called as the stage 2. So if two buffers are used at two different locations along the line, then a three-stage line is formed. So suppose if you have 12 workstations in line, if you place a storage buffer after every 4 stations, that means you'll have 2 storage buffers and 3 stages. So for an n stage line, there will be n minus 1 buffer storages. You can have maximum n minus 1 buffer storage. For example, if you have 10 workstations, you can have 9 buffer storages. That is one buffer storage after every workstation, one storage buffer in between two workstations. So if you have 10 workstations, you can have maximum 9 buffer storages. So considering a two-stage transfer line with storage buffer separating the stages, Let us suppose that on an average the storage buffer is half full. Okay, we will continue from here in the next class. So I will stop the class here today.
No, but the syllabus about the first I
Syllabus for the first I is not changed. It remains the same. That is the first unit complete, and the second unit is going to be only till control functions. The analysis part is not included. So the syllabus remains unchanged. First unit full and second unit till control functions. No analysis.
okay, ma'am.
Okay.
Ma'am, problems also will be there, no, ma'am? Mathematical model equation.
Yes. First unit complete. Whatever Vinayak sir has discussed, whatever I have discussed in the first unit, all of that will be there. And also second unit till control functions. Also, there
Yes,
are
ma'am.
quiz questions that you need to answer.
No, ma'am.
Yeah, for your I, you'll have to answer quiz.
That's yes, ma'am.
Yeah. Okay, so we'll continue. You'll have class on Tuesday.
No, ma'am.